L over K, finite, is called Galois when it satisfies any of the Theorem 4.1 criteria. Criterions. And when L over K is a Galois extension, the group L over K is called the Galois group. So let's say in this case, ought L over K is the Galois group of L over K.
When L over K is a Galois extension, the group
Is the group of the Galois extension is the K-fixing automorphisms of L. All right. All right. Let me yet again try to state the fundamental theorem. So looking ahead, like where we are right now, we want to state the fundamental theorem, and then we need to look at the particular ways that Galois extensions can be made, and that will lead us to an understanding of the impossibility of solving the quintic. All right, let's see here. So this is the fundamental theorem, which is his section 5 in the Galois correspondence here by Keith Conrad. Now, before he gets to the fundamental theorem, he has a theorem by Artin, which I feel like we already have. I don't know. E a field and H a finite group, finite subgroup of the automorphisms of E if finite. All right. If the degree of E over the fixed field of H is finite, then E over EH is Galois. With the Galois group of E over EH is just H. Again, this theorem is due to Artin. See if he's got an example of it. Yeah, no. And then he has theorem 5.3, let E be a field, H be a finite group of automorphisms of E, then the extension E over EH is finite. Oh, okay. So actually there's an improvement on this theorem which says that the finiteness condition is unnecessary, because if you have a a finite group of finite subgroup of the automorphisms, you're going to be given that the degree of EH over E is finite. So theorem, anyway, so there's that. Let's see here. Now here's the fundamental. These are not the fundamental theorem yet. This is the fundamental theorem that I'm about to write here. Theorem 5.6, and this is Mr. Galois himself. Sorry, you got me doing it now. Let's see here. Let K over F be a finite Galois extension. Oh, yeah, L over K is what I meant. With G equal to the Galois group of the extension. Oh, L over. Sorry.
No, you're good.
Then, yeah, it's the side effect of using Dummett and Foote and this, right? He's got different choices of letters usually. Then the inclusion reversing mappings. You know, F, gal, L over F, and H maps to a fixed field of H between intermediate fields of what? I should say between what? Between K and L, right? And the subgroups of G are inverses of each other. And satisfy the following properties. When what? When F and H correspond. What does that mean? F and H correspond. That would mean that F is the fixed field of H, and it would mean that H is the Galois group of L over F. All right. And what are the properties? What properties do we get? We get A. Where'd my blue chalk go to? There it is. A. We get the number of H. In other words, the order of H, right? The number of elements in H is the degree of L over F. And the degree of F over K is equal to the degree. Now you got to be careful here. What does this mean? Degree of G over H. That's not degree, is it? This is a notation that it's the same notation, but has a radically different meaning. Two intermediate, so I'll tell you. So that is the number of H cosets in G. That's group cosets. So the number of cosets versus, remember Lagrange's theorem? Goes back to that. And this, of course, is the degree of F as a vector space over K. Right? So field degree is a vector space dimension calculation. Oh, it's the dimension of F as a K vector space. Right. And the other one is the number of, so this is dimension with respect to scalars in K of F. And this is number of H cosets in G. Now B is a little bit more technical. Two intermediate fields. If you have intermediate fields F and F prime, and corresponding H and H prime under the correspondence, right? So these are isomorphic. So F is isomorphic to F prime, all right? If and only if H and H prime are conjugate.
Don't we usually say that they're conjugate to respect or something, like S conjugate?
This is conjugate subgroups. I can't spell. Conjugate. What does conjugate mean? That means that, to be explicit, that means that the Galois group of L curses. Where's this sigma coming from? That feels like a typo. I hope I'm right. So I mean, conjugate subgroups means that they are related by conjugation, I suppose, when we say it. But let's see here. See, he's got gal of L by sigma. What is sigma F? Would that even make sense? Sigma of F? Sigma of F. I don't think sigma of F makes sense. Well, anyway, I think this means H prime is equal to sigma H sigma inverse for all sigma in G. That does not has to be. It doesn't have to be for all sigma in G. For some sigma in G, there exists sigma in G such that, right? So you can get from one subgroup to another by just conjugating. But if we put down what that means in terms of the fixed fields, this is what? This is gal what? L over F prime, right? Sigma gal L over F, right? Sigma inverse. So he's got a sigma of F here that doesn't make sense to me. And then C, I wish I could just not, you have these, I wish this would still be on the board. I don't have to rewrite it, you know? F over K is Galois. If and only if H is a normal subgroup of G, in which case right, the restriction map G restricts to gal F over K, where sigma maps to sigma restricted to F is surjective with kernel H. So G, the factor group of G by H is isomorphic as groups to the Galois group of F over K. So let me put that into words.
Is that the first isomorphism theorem right there that they're going off?
No. I mean, that's involved, but that's part of it. But does this involve the first isomorphism theorem? Sure. But it's got...
Yeah, because I was like, this is a lot to unpack here.
Yes, but let me put it into words. So what this is saying is that if you have an extension, if you have an intermediate field, right? And that field is F, right? That is a Galois extension over K only if the corresponding subgroup of the Galois group of the entire extension, right, L over K, which is G, is a normal subgroup.
So we have F between L and K, and that is considered a Galois extension if K is a normal subgroup of
Let's see here. We had
you have K up top, F, and then L. I think. No, L, F, and K.
yeah. So like, let's see here. L. Let's let L be equal to Q adjoin the. I'm thinking of the one that had the curses. The cube root of 2,
Yeah.
which we'll call rho, and rho, where rho is the e to the 2 pi I over 3, right? And then we had different things, right? We had like Q, let's see here. There's also a, you can figure it out that that the Q adjoin row is one of the subfields, right? But then there's the Q adjoin cube root of 2, right? There's the Q adjoin row root 2, and there's the Q adjoin row squared root 2, right? And of course, these are over Q, right? Now, so here I'm saying Q is my K, right?
Yes.
So, and what are the corresponding groups? We've got,
Oh, I have the picture. I should have it. Is it this one?
Yep. So we've got the identity group, and then we've got then the one just generated by sigma, and then these three over here that are generated by tau, sigma tau, or sigma squared tau. And these are all over G, which in this case is generated by sigma and tau. And it's basically the symmetric group on three things. Those three things are specifically the zeros of the polynomial x cubed minus 2. So x cubed minus 2 splits in L, right? L of x allows you to factor x cubed minus 2. All right. So that means that K over L is a Galois extension because it's a splitting field. That's one of the four. It's Galois. The question then is, the question you can ask though, is Q adjoin row Galois over Q, right? Is Q adjoin the cube root of 2 Galois over Q, right? We can ask about the intermediate fields here. Are those themselves Galois extensions? Maybe, maybe not. So, so what did we have? C F over K is Galois if H is a normal subgroup of G. What are the normal subgroups of the symmetric group on three things?
Normal subgroups? I actually don't know.
So remember, one of the theorems we have is that if the index of a subgroup is 2, it's normal. So what's the index? It's the number of cosets. By Lagrange's theorem, it's the order of the group divided by the size of the group. So like, remember that the order of sigma is 3. So that means that this guy, right, is a normal subgroup. So I put H equal to this. This is a normal subgroup because the index the index of H is 2, right? So like explicitly here's what's going on, Audric. H is itself 1 sigma sigma squared, right? Tau H is the other coset. It's tau sigma squared. Those are your two cosets. They're disjoint. The union of those two gives you the whole group as 3. So H is normal. And that means that the corresponding extension field is Galois. And not just that, its degree is the same as the number of cosets, right? So that tells us that if that's H, what's the corresponding fixed field to this H is what?
This corresponding fixed field?
Like, yeah, what's the fixed?
Okay.
This is LH, right?
Yeah.
So this has degree 2 by part A. The number of cosets of H is the degree of the fixed field of H over K. Now, of course, we also know from previous calculations that Q adjoin rho is actually Q adjoin I. So yeah, that's a degree 2 extension, right? And we also learned today that any degree 2 extension is Galois.
Yeah.
Because it's normal. Assuming separable. I need the separable condition, I think, but as long as we're not in characteristic 2, we stay out of trouble, I believe. All right, now flip side. Are any of these extensions Galois? Are any of these extension fields Galois? They're not, because any subgroup of order 2 in S3 is not normal. If you take like any of these subgroups, and suppose you conjugate it by, let's say, sigma. What happens when you conjugate this by sigma?
I'm not sure. Do you get
Yeah, I mean this by this.
Do you get another subgroup back?
So we get like 1. We get sigma inverse from the 1, right?
Mm-hmm.
And then we get sigma tau sigma inverse, but sigma inverse is sigma squared, right? And remember, tau sigma is sigma tau.
Yeah.
So this is 1
tau.
1 tau. It's just 1 tau. Okay, yeah. Maybe tau sigma actually. No, that's tau sigma. See, because that gives me sigma tau is tau sigma squared, right?
Yeah. Oh yeah, and so yeah.
So one of them's left over. You get 1 tau sigma. The point is that so I know you're not super fresh on the like normal subgroup stuff, but a normal subgroup, one of the criteria for normal subgroup is that if you conjugate a normal subgroup, it goes back to the same subgroup again. That's another way of saying the left and the right cosets are equal. But in practice, the conjugation criteria is more often what we see in applications of group theory. So it's a better way to, in some sense, it's a better way to characterize normal subgroups. But yet, in the introductory class, we tend to say left-right cosets are equal. The point is, this is not a normal subgroup. And similar calculations will show that neither are any of these. None of these are normal subgroups, which means that the corresponding extensions are not Galois over Q. And of course, we already know that from our basic example. We found that the number of automorphisms, Q-fixing automorphisms of this extension field was just 1.
Yeah.
But the degree of this extension is 3.
Yeah.
Right? But the Galois theorem is not silent on this example either. It says that, you know what? That those are isomorphic because, by the way, these are isomorphic because, by the way, these groups are conjugate.
Yeah.
Well, you just saw that this is conjugate to that.
Yeah.
Or that, I forget whichever, right? But so, in other words, these are isomorphic because these are conjugate subgroups. But on the other hand, these are not Galois over Q
Yeah.
because there's various ways you could look at it because they don't have the full group of automorphisms.
Their subgroups aren't normal.
Yeah. So I'm sorry. I know. I'm sorry. I went over a couple minutes, but I wanted you to see an example of the theorem before we just stop for today.
No. I was letting you go because I wanted to finish this. Okay.
But if you really understand this example and how it works together with the theorem, that's like a lot of it. Like, so anyway, going forward, like in Dummett and Foote, he's got a section on finite fields, which I'll probably skip, and then he's got a section on composite and simple extensions, which I'll treat very lightly. And then cyclotomic extensions and abelian extensions. We all find something in there to talk about. But what I really want to get to, hopefully next time, is to start looking at the Galois group of polynomials. And there we get to look at the elementary symmetric functions. And then I want to say that get this really beautiful setup. And then the section after that, he starts talking about the solvable and radical extensions. And what we'll learn is that describing the extension fields as being solvable. Well, we can talk about. The thing is, with this correspondence, we can characterize the nature of extensions by corresponding properties of the groups. And it turns out that having an extension which corresponds to having a formula, like a quadratic formula, it corresponds to having a group structure, which is a particular one.
Oh.
And so if your Galois group doesn't have that structure, it means that you can't have that kind of extension, and hence you can't have that kind of formula. That's ultimately the structure of Galois' proof of the insolvability of the quintic for certain examples, but not all. Some quintics can be solved by radicals. Anyway, that's where we're going.